Okay, so in our last class we had discussed the flow over an impulsively moving plate. So this is the flow over an impulsively moving plate, right? And we had obtained a solution. So the solution was something like, what was it? 2 by root pi 0 to 2 root nu t, right? Right. So this was our solution. And now, so I was discussing towards the end of the class that there is a length scale called root nu t, which is the so called penetration depth, also it is called often. Okay, basically it means how far off has the effect of plate penetrated inside the fluid after time t has passed. Okay, after time t has passed, how far off the fluid has the effect of plate has penetrated inside the fluid. And we see that for large nu t, for very large nu t, when y is very large compared to nu t, this integral is approaching 1, right? This integral is approaching 1. So 1 minus this integral is approaching 0. So for very large nu t, the velocity is very small. The velocity is very small compared to u naught. Okay, so velocity of the fluid is very small compared to u naught. Now there is an interesting point here to make, and that is this square root of nu t is the intrinsic length scale of the flow. What it means is that there is no externally imposed geometry. If you think about it, there is no externally imposed geometry or geometric scale in this flow. Okay, if you think about it, there is absolutely no length scale that we have imposed in the flow, because the fluid is extending all the way till y tends to infinity. Okay, and it is starting from y equal to 0. So that means the only length scale in the problem is the integral length scale of the flow. If there was no flow, there is no length scale. Okay, you can think about it like that, that if there was no flow, there is no length scale involved here. Okay, so in these kind of cases, similarity solution usually will hold. You will, this is like a first hint to you that if your geometry does not impose any length scale, then the similarity solution might exist, because the flow doesn't see any geometric scales that are externally imposed. For instance, if I had, instead of this situation, so this question is in your practice sheets also. So let us say I had this situation. So you have a separation between two plates. So this is a fixed plate. Okay, the separation between the two plates is, let us say, d, and you start moving the bottom plate in that case. Okay, you start impulsively moving this plate, but there is a top plate. Now in this case, there is an externally imposed length scale, which is d, which is the separation between the two plates. In this case, you will see that similarity solution usually does not hold. Okay, and the standard technique of variable separation works in these cases. So you can write down the same governing equation you will have for this case also. Okay, and you can solve this problem by assuming the separation of variables, and then you can solve that this is t prime by t equals nu y double prime by y. Okay, so the left hand side is purely a function of time, the right hand side is purely a function of y. So the only way these two can be equal is if they are equal to some constant, let's call it lambda square. I'm not saying anything about lambda being real. Okay, lambda could be imaginary also, so this lambda square could easily be a negative quantity or even some complex quantity. I'm not saying anything about what lambda is. Okay. Make sure the count matches. It's very easy today to match it. No? So, so the solution that we get from here is, so you have t prime equals lambda square t, which means t should be equal to some constant times e to the power lambda square t. Okay. Now we know that lambda square, if lambda square is greater than 0, then t grows unbounded. Okay, for t tends to infinity, this solution will grow unbounded. We cannot have that. We cannot have an infinite velocity in such a situation. Okay, this is not a physically unrealizable situation. You can imagine that you cannot have infinite velocity here. So lambda square greater than 0, t grows unbounded. So this is not a valid case. That means lambda square has to be less than equal to 0. So we will take lambda square is minus k square, and I will write that t is a e to the power minus k square t. Let us write lambda square as minus nu k square, just so our algebra becomes easier. You will see why. This nu will cancel out, so my algebra will become easier. Okay, nu is anyways a positive constant, so it does not matter. So now solving this, nu y double prime over y equals minus nu k square. So that means, what are the possible solutions of y? What are the possible solutions of y? So y double prime equals minus k square y, sine and cos, right? Or we can write c e to the power I k y plus d e to the power minus I k y. This is the general solution of this equation. Okay. Now what we do is we have to find the possible values of k for which the boundary conditions will be satisfied. So you have u equals 0 here on the top, and you have u equals u naught for t greater than 0. So if you want to apply that, first of all let us write a general solution. The general solution is, so one thing that I missed here is writing this whole thing. It's different when k equals 0. When k equals 0, your t equals a constant and your y is actually some c naught plus d naught y. Okay, this k equal to 0 case is important. Okay, because if you put k equal to 0 here, you will get constant. That is not the case. Okay, good. Can you stop the recording? Lambda or k equal to 0. Okay, you can sit. Thank you. So k equal to 0, we have this solution, and the overall solution of this velocity actually looks like c naught plus d naught times y plus all the values possible for k e to the power minus nu k square t times c e to the power I k y plus d e to the power minus I k y. Now what happened here, if you think about it, what just happened here? We had found some valid solutions which satisfy this governing equation. Okay, we had found valid solutions which satisfy this particular governing equation. Since this is a linear equation, the overall solution is a linear combination of these. Okay, that is what the essence of separation of variables is. When you separate the variable, when you separate the variables y and t, and then you find these different solutions, they are not going to be valid for all cases. Okay, for all case these are not going to be valid. There are going to be some specific values of k for which this is valid. And what we have seen, what we have found is, we have written down this, and these c and d actually, they are functions of this k. Okay, so now let us think about what are these constants going to be. Okay, let us think about what are these constants or these functions of k, how can we evaluate them. Yeah, they are arbitrary. They will change for every value of k, as we will see. They are arbitrary, not completely arbitrary, okay, because we have to satisfy the boundary conditions. We will see that in a minute. Okay. Yeah, of course, that is true, because k equal to 0 we have already accounted for separately here. Okay. So now let us see how to evaluate these constants. Now the first way that we are going to move forward is there a way that I can evaluate this particular part ignoring this? So when will this whole term be 0 for sure? When will this whole term be 0 for sure? But that depends on the values of k, ck and dk. Let us say irrespective of whatever values of k and ck and dk are, when will this whole thing be 0? In the limit t tends to infinity, this guy is going to make sure that things are 0 here. Okay, what is this limit t tends to infinity? Which kind of solution do you think we will have when t tends to infinity? Steady state solution. When we have limit t tends to infinity, we have a steady state solution. You have u y t equals c naught plus d naught y. What is that steady state solution for this case? This is a Couette flow. This is a Couette flow solution. Okay, this is that linear solution that you have. So c naught plus d naught y in the limit t tends to infinity. This also has to satisfy the boundary conditions. So u of y equals 0 will be u naught, which means c naught is u naught, and u of y equals d will be 0, which means u naught plus d naught times d is 0. So that means d naught is minus u naught over d. Okay, so u of y comma t is u naught 1 minus y by d plus sigma k e to the power minus nu k square t c k e to the power I k y plus d k e to the power minus I k y. So we have found these c naughts and d naughts at least. And now how do we move forward? We have to substitute the initial and boundary conditions. So I had written this system. The initial conditions are that initially there is no flow. The boundary conditions are that y equal to 0, it is u naught, and for y equals d, it is 0. We have to satisfy these three initial and boundary conditions, these three conditions together. So when I put y equals, let us say, let us put y equals 0. Okay, what do we get? For y equals 0, hmm? What do we get? Y equals 0. Hmm? At y equal to 0, u of y t should be u naught. So this means sigma k e to the power minus nu k square t c k plus d k should be 0. For all times, this summation must be 0. Okay, for all times this summation must be 0. That means for individually for each k, ck and dk will have to sum up to 0. So that means for all k, ck equals minus dk. Okay, for all k, ck is equal to minus dk. So we get one simplification in the solution when we have put y equals 0 boundary condition. Now let us put y equals d boundary condition. What do we get for y equals d? So we have u y equals d is 0, and what do we get here? Here also we get 0, and again we will get that for all, sorry, this is nu k square t. So ck e to the power I k d minus ck e to the power minus I k d, this has to be 0 for y equals d boundary condition. So for all times this has to be 0, that means this is 0, which means what? This is what? 2 ck sin 2 I ck sin k d. Okay. There are two ways to solve this. One is ck equals 0, that is a trivial solution, right? Ck equals 0 is trivial solution. That is like, yeah, there is one solution that satisfies this equation when u is 0, makes no sense. So ck equals 0 gives you trivial solution, which is useless for us. The other is when kd equals plus minus n pi, and here we start getting the possible values of k. Okay. So this is k, this means k equals plus minus n pi by d. These are called the eigenvalues of the problem. The reason why they are called eigenvalues is because, as we will see later down in the course, this can be written like a differential eigenvalue problem. Have you guys looked at Sturm-Liouville eigenvalue problems in maths? So this can be looked at like that. Okay, when I convert this PDE into ODE by assuming this separation of variables, then basically I have obtained two eigenvalue problems, and these are the eigenvalues for of the problem, not the equation. If you change the boundary conditions, your eigenvalues may change. Okay, boundary conditions are important for the problem. This is what you have for your problem, not just the equation. It's for the whole set of equation and the conditions that we are imposing. Okay, so we have eigenvalues of the problem k like this. Now we have the possible values of k over which we have to sum things over, and the solution is the solution is you can write it as sigma over n, and we can write e to the power minus nu k n squared t, and then we know that c and ck and dk are related, so I can write it as 2 I can bring outside, and then we have ck sine ky. So we still have this ck to evaluate, and to do that we use our initial condition, which we have not used so far. So u at y comma t equal to 0 is 0. So that means u naught 1 minus y by d plus 2 I. So t is equal to 0. So this exponential term is 1. So we have ck sine ky, k n y. So that means sigma n ck sine k n y is minus u naught by 2 I, 1 minus y by d. How do we solve for ck from here? Hmm? How do we solve for ck from here? Hmm? How do we solve for ck from here? Huh? Y equal to pi by 2, to k and y equals pi by 2. So for a specific y you will have, but then you will have summation over n. So you cannot solve for individual ck n. So how do we solve this? Okay, that's a very specific and a very good answer. We use the orthogonality of the sine kn. So we know that sine n pi by dy times sine m pi by dy integral from 0 to d. Can you evaluate this integral? What is this integral? Hmm? When m is not equal to n, so these two are different, then you can write it as cos of n plus m pi y by d minus cos of n minus m pi y by d, and then when you integrate this over, for this value cos will give you what? How will this be not 0? Okay, so let's write it, let us write this thing. So we have 0 to d cos of n plus m pi y by d, so half I'll put, and then what do we have? Actually minus of this plus cos of n minus m pi y over d. So this integral we have to evaluate. So cos n minus m pi y by d and cos n plus m pi y by d. Okay, when you put y equals d, then you will get, what will you get for this integral? Hmm. So this will give you sine of n minus m pi y by d over n minus m pi. Okay, and then you will have n plus m pi sine n plus m pi y by d from 0 to d, 0 to d, both of these are 0 on both 0 and d. So this integral is actually 0 for n not equals m, but when n is equal to m, when n is equal to m, then what can we do? This becomes sine square n pi y by d. Okay, this case, particularly this case, is singular when n is equal to m. So we have to evaluate this in the limit of n becoming equal to m. Okay, so some students say, oh, but this relation is not specific to n being equal to m or not. Yes, you are right, but the integral eventually that you get will be singular. If you put directly n equals m, you will get 0 by 0 form. Okay, so you have to evaluate it in the limit of n tends to m, or you can just substitute n equals m here. You will get 1 minus cos 2 pi y by d. Okay, you will get a 1 minus cos 2n pi y by d integral dy half 0 to d. What is this integral? This will give you d by 2. Okay, this will give you 0 d by 2 because this is 2n pi y by d. So from y equal to 0 to d, there is one full cos. Integral of one full cos is 0, right? You will have one full cos, two full cos, three full cos based on n, all of their integral will be 0. So this is equal to dy 2. So that means this integral is basically equal to 0 if n is not equal to m, and it has a constant value when n equals m. So what we do is, just like we evaluate the coefficients in Fourier series, we multiply on both sides by sine k m y and we integrate from 0 to d. So when you are integrating this from 0 to d, basically on the left hand side you will have just one term that survives. Okay, when n becomes equal to m, only that term survives, all other terms become 0. Okay, so the left hand side will give you that you are trying to evaluate basically ckm times d by 2, and the right hand side is minus u naught by 2 I 1 integral of 1 minus y by d sine km y dy, integral from 0 to d. And you can solve that integral and evaluate the values of sine km, oh ckm. Okay, you can evaluate the values of sine ckm. So ckm is minus u naught by I d, and this finishes our solution. Basically, this gives us the solution of the problem that we were looking at. If this is the first time that you are looking at the variable separation method, then I would recommend you to go through your maths courses textbooks, particularly textbook by Krasig on mathematics for engineers. You should look at the textbook from Krasig and you will see tons of problems of this type. Okay, variable separation is is a very common method for solving linear PDEs in engineering. So in the notes, as you will see, there is a cylindrical counterpart of the impulsively moving plate problem given. So that is, let us say you have a cylinder, okay, you have a cylinder of some radius r that starts to move impulsively or starts to rotate impulsively at an angular speed omega, and this cylinder is in an infinite fluid, okay, in a medium that is infinite. So for r tends to infinity, you have a fluid. Now in this particular case, what do you think? Is there going to be a self similar solution possible? Is there a self similar solution possible? In the beginning of class, what did I say? When do we expect a self similar solution to be possible? No, no. What did I say in the beginning of class? There is no external length scale imposed. Is there an external length scale imposed here? Yes, the radius of the cylinder. No, fluid is outside, but fluid is not going all the way to r equals 0. Fluid is restricted to small r equals capital R. There is an external length scale that is imposed, and that is the length scale of capital R. Huh? Yeah, semi infinite and infinite, but there is an external length scale also involved here. That is the main catch here, that there is an external length scale involved in this particular case as well. Okay, there is an the solution for this and solution for a, let's say, larger cylinder, they are not going to be, I mean, physically they are not going to be same. Okay, so in this case, you should solve your Navier-Stokes equations in the cylindrical coordinates, okay, and you should know what Bessel's functions are. So the particular reason why I have given this in the notes is so that you can look at it, you can go through each and every step carefully and know what Bessel's functions are. Bessel's functions are useful for doing whatever we have been doing in Cartesian geometry. The moment you bring those problems or equivalent of those problems to cylindrical geometry, you do get Bessel's functions. Okay. And you can have a counterpart of that, as one of your friends said, the fluid being inside a cylinder. So it's like a drum which starts to impulsively rotate at uh, angular speed omega, and you have to solve for flow inside the drum. Even that is solvable through Bessel's functions. And in that again you will see fluid is bounded, the flow is bounded, there is an external length scale imposed which is capital R. Okay, so you will not use the cell similar solution, you will use the variable separation method. Okay, so these are all 1D problems, 1D problems in the sense that you have unsteady flow, but the flow velocity is still varying in one direction. Now let us shift our focus to some 2D problems. First we will look at 2D steady problems. So the classic 2D steady problem in fluid mechanics is flow through pipes. Classic 2D problem is flow through pipes, and here I do not mean necessarily just give me a second. Here I do not mean necessarily flow through pipes which have a circular cross section. Okay. The kind of pipes that we may have are could be like this, where you have a rectangular cross section, you could have an elliptical cross section, okay, not necessarily circular but elliptical cross section, you could have triangular cross section as well, and you could have any other combinations of cross sections, you could have some arbitrarily shaped pipe. Okay, for this particular case now we are not going to look at what if this cross section is also varying along the length of the pipe, we will do those kind of cases later on, but for now we will assume that the cross section is constant along the length of pipe. Okay, and we will try to first get some general characteristics of the problem irrespective of the shape of this cross section. So, what we are going to assume is that the flow is only in z direction. So, it is a unidirectional flow, we assume a priori that the flow is unidirectional. So, this is your z direction and then this is your x, this is your y. So, flow is in z direction and so u basically is 0 comma 0 comma some w. Okay. And once we assume this, from continuity you have this flow is only in z direction. So, these guys are 0. So, which means del w by del z is 0. So, this means it is a fully developed flow. Okay. We are also looking at steady flow. We are also looking at steady flow. So, that means this w is just a function of x and y. Okay. This w is just a function of x comma y. So, since flow is only in z direction, from x and y momentum equations you will get, so from x and y momentum equations you will get del p over del x is 0 and del p over del y is 0. So in exam you cannot just write like this, you have to show, okay, you have to write the governing equation, you have to show that hey, all the velocity components are 0, so this is what you get, okay, you cannot just copy this down. So from here we get that pressure can only be a function of z. And so now looking at our z momentum equation, we have del w by del t plus u del w over del x plus v del w over del y plus w del w over del z equals minus 1 by rho plus nu. So we are looking at steady flow, this is 0, there is no u, there is no v, there is no del w by del z, there is no, oh sorry, this is not 0, there is no del w by del z. So eventually we get that 1 by mu dp dz equals del 2 w over del x square plus del 2 w over del y square. So this is particularly in your Cartesian coordinates, okay. So in the Cartesian coordinates we get that for flow through any of these pipes, we have del 2 w over del x square plus del 2 w over del y square equals 1 by mu dp dz. So this is a function of z, this is only a function of x and y, they can be only equal when both of them are constants. Okay. So that means we have to solve this equation in Cartesian coordinates, we have to solve this equation for w with the boundary conditions that this w is 0 on the cross section boundary, okay, with the condition that w is 0 on the cross section boundary, there is no slip here, all of these walls, these are hard walls. So this equation needs to be solved with the condition that w equals 0 on the wall or walls, if you have, if you are considering them multiple walls like in cylinder, in the square or triangular cross section. So there is a very interesting way of solving this equation, and that is I don't need to solve for w, I can make another auxiliary function which satisfies a simpler equation than this. So if what would be the simpler equation if this was equal to not a arbitrary constant but 0, okay, and I can formulate that by recognizing that let us say I write a function psi where, or let us say I write w as some psi plus c1 x square plus c2 y square plus c3 xy plus c4 x plus c5 y. An interesting thing about this function is that the Laplacian del square by del x square plus del square by del y square of this of this function, what is it? What is the Laplacian of this function? 4c1, 2c1 plus 2c2. It's a constant. Laplacian of this function is a constant. Okay, these c3, c4, c5 are arbitrary, they can be whatever, Laplacian of this function is a constant. So if I pick my c1 plus c2 such that c1 plus c2 equals half of this constant, Okay. So, let us say you have del square W, which should be equal to 1 by mu dp dz equals this del square psi plus 2 times C1 plus C2. So, if we pick 2 times C1 plus C2 equals 1 by mu dp dz, then that means psi satisfies the equation, this guy. Okay, psi satisfies an easier equation compared to this where you have a constant. Psi satisfies this easier equation. The reason why I say this is easier equation is it is easier when you have Cartesian coordinates to deal with in 2D. Okay, you guys have not done complex calculus, but if you had done, then you would have recalled that this is your Laplacian equation, which is solved, which is which holds for the real and imaginary part of any complex function which is is differentiable. If you have a complex function that is differentiable, it's twice differentiable, its real and imaginary parts satisfy this equation by definition. Okay, by definition, we will look at that when we look at potential flows later on, but for now I will just mention it and not prove it for you. If you want the proof, you can go through the notes that I have uploaded. But कर लो यार, C6 भी कर लो, उससे क्या फर्क पड़ेगा, कांस्टेंट से तो कोई फर्क ही नहीं पड़ता हमें. Why would you add a constant?
Because you want to make the Laplacian of that term to be zero.
So what, C6 is anyways not helping anyway, right? W is also supposed to be 0 on the walls, so C6 anyways you will probably get that it is 0 on the walls. But sure, you can add a constant also, constant doesn't really change anything. Yeah. No, I am saying that let us say W is a combination of these two functions. No physical significance as of now. Okay. No physical meaning. It's just an auxiliary function for us which is helping us solve this equation. No, no. How can psi be complex? Psi cannot. No, no. What I was saying is, if you have a function f of z and it has some real part plus imaginary part like this, then both these phi and psi, they satisfy the Laplacian equation if this f is twice differentiable. If this f is twice differentiable, then both of them satisfy this Laplacian equation in 2D Cartesian coordinates. To simplify this equation, because this equation I know how to solve using separation of variables. This equation is not so straightforward to solve using separation of variables. Okay, as you will just see now that even in the case of let us say a rectangular cross section. So this is your rectangular cross section, let us say, and this length is, let's say, b, this length is a. So if you want to solve this, if you want to solve this, the flow through a pipe which has this kind of a cross section, okay, then what we will do is we have to solve this. So what we will do is we will say let W equals psi plus y square minus a square times a constant. Okay. So I have added this y square minus a square because if some of you were thinking, you would be saying that okay, you have simplified the equation for psi, but now the boundary conditions for psi are nasty. The boundary conditions for W here were easy. Once you substitute for any general C1, C2, C3, C4, C5, C6, the boundary conditions of psi will be very difficult to formulate. Okay, so we should try to formulate a function here which helps us in defining the boundary conditions as well. And as you will see here, when I put y equals plus minus a, this helps me simplify the boundary conditions at least on these walls as well. W equals 0 on y plus minus a, so psi is also 0 at plus minus a, because this guy is 0 at plus minus a. Okay, so this involves a lot of hit and trial, you may think, but it's eventually to make our algebra further down easier. Okay, so we'll say that W is this, and here if del square W has to be equal to 1 by mu dp dz, then that means del square W is, we will say that C is equal to 1 by 2 mu dp dz, and del square psi is 0 with the boundary conditions. So, what were the boundary conditions here? W at x equals plus minus b for all y is 0, and W at x for all x y equals plus minus a is 0. This time for psi, our boundary conditions will be x equals plus minus b for all y, W is 0, so psi is minus of this, so minus 1 by 2 mu dp dz y square minus a square. And what is the other boundary condition? Psi for all x y equals plus minus a is 0. Since W is 0, this function is also 0. So, whenever we are solving this 2D equation where you have this del square by del x square plus del square by del y square equals a constant, this is a very standard trick in 2D PDEs. The trick is that you want to remove that constant, you want to get a 0 there, and to get that 0 you eventually end up putting some function in the boundary condition. Okay, and as some of you might have already realized, as we did in our previous example, that function will help us break down a Fourier series coefficients, will help us determine some Fourier series coefficients, as we see soon, maybe in the next lecture. When we solve this equation del square psi equal to 0 using separation of variables, okay, we will get some Fourier series. Eventually we will get some Fourier series, and this function will help us get the coefficients of those Fourier series. Okay. So, if I had it x square minus b square, then this wouldn't be 0 and this also wouldn't be 0, right. I can make only one of them 0. If I add another one, then both of them will not be 0. You can solve in that case also, okay, but the solution will be, the solution methodology will be very complicated. I mean, the algebra will be 5 pages long instead of 2 pages there. So, it's a choice. Okay, we'll cover the rest in next class.